Okay. All right. And just want to check if everyone can hear me or not. Maybe say yes in the Zoom chat. Hello, hello. Yes. Okay. Thank you. Thank you so much. Yep. I will get started now. Welcome everyone to Fit 2107 Software Quality and Testing. I hope everyone had a good mid-semester break and enjoy the FL, the public holiday, the match as well. And today, this is week 10 already. We're gonna talk about software metrics. Okay. Yeah, as part of the this unit. So before we talk about the software metrics, we will need to understand like why it is so important. What are these metrics? Why and how can we measure it? You know, there are different types of the metrics. So I will walk you through every types of the not every types, but most of the key important software metrics that we are using in software engineering. All right. So probably before we get started, I should talk about this quote, from Peter Drucker. If you cannot measure it, you cannot improve it. So I think before we manage any software projects, we should be able to measure what is the goal, what is the measure, how can we improve it, that kind of thing. But as long as we cannot measure it, we cannot improve anything, But I think the key question is that what should be measured? Yeah, so we will talk about that in this lecture. All right. But what do we mean by software metrics, right? Basically, metrics refer to the standard of the measurement. Let's say in terms of the time, we often use the second, minutes, or hours. In terms of the length, we use the meter, foot, or whatever. And these are some measurable metrics, right, that we can use to measure things. But in terms of software, we can also measure as well. But can you think about what kind of aspect that should be measured, and what are those measures, right? Okay. Yeah. So in software engineering, it is also an active research area as well. I just want everyone to look at the bottom right figure here. So I found this figure capture the four main dimension, four main aspect of the software metrics that we are normally use in software engineering or for the project planning. Okay. The first category, the highest level, we should look at the project level, right? In terms of the project level, examples of the measure could be how long does it take to run the project, how long does it take for each phase, how many bugs that are found at each phase, that kind of thing. This is at the project level. How many people are within the project, how many engineers, that kind of thing. We can also look at the people metrics as well. For example, who are the active developers, who are the non-active developers, who are the core contributors, who are the manager, and how many commits that they have contribute to the project, how many bugs that they introduce, that kind of thing. Okay, this is the software metrics at the people level. And we can also look at the process level as well. And process, we can look at the mainly, can be like what is that? The GitHub, no, sorry, the software development process. We can also look at the code review process. We can also look at the software testing process. For example, development process, how many commits that occur within that repo within this period, how many, what is the size of the commit, how many lines of code, how many lines are changed for each commit, how many reviewers that have already reviewed the code, reviewed the commit, how many and in terms of the software testing, it can be how many test cases that have been written, how many what is the code coverage, what is the test effectiveness, that kind of thing. CI/CD build can be measurable as well. Most of the time, how many CI builds are success, how many CI builds are fail. These are the metrics that we use in software companies, right? And in terms of the product, what is the size of the product? How many lines of code? How complex it is? We talk about the psychrometric complexity before. Okay, so throughout this lecture, we're gonna go through each of the metrics one by one. Okay, yeah. But the key question is that why do we need software metrics, right? So in general, this is like a because we use the software metrics to help making decisions. Okay, most of the time in software engineering, it's all about decision making. For example, as a manager role, most of the question that we often ask the development team is that when should we release the product? We need to release the new feature as much as possible, as soon as possible, right? But when should be released? And then we cannot release the products without measuring the other things, right? For example, as a developers, how many bugs are there? Have we fixed everything or not? Have we implement all of the new features requests or not? That kind of thing, right? As a QA engineers, they often ask themselves as well, which modules should I test first? Let's say software has different components, different modules, Wi-Fi, network, or whatever, right? But which one they should test first? Let's say there are 100 bug reports right now. Which one should they fix first? That kind of thing. It's about prioritization. There are lots of things, but that they should have some other measurement as well to prioritize, right? Like which one they should do first. As a designers, they often ask like, is software design good enough or not? And how can we measure the software design? That's why we have like a object-oriented matrix, whether the software is highly coupled, it is cohesion, how good is that kind of thing, you know? As a tester, how effective is our test suite? How can we measure the test effectiveness? How can we measure the code coverage? We talk about different types of the code coverage already. That's why these are the software metrics, software measurement that we often use nowadays to measure whether what we are doing is good enough or not. All right. Okay, where metrics are used? We often use in the project monitoring. We monitor the whole project, right? We can use to control the project as well, whether we are on the budget or not, that kind of thing. We can use the metric to plan a new project, estimate the cost. We can analyze the profit of the testing, the cost, the quality of the products as well, given the products at the moment with this amount lines of code, with this OO metrics, object oriented, with this amount of complexity, what is the likelihood that it will introduce bugs in the future, that kind of thing. So we can often use this metric to build prediction as well, machine learning model, AI models, that kind of thing. Okay, that's my active research area. That's my research area. Okay, yeah. That's so if we look in terms of the quality metrics, right? There are different aspects. When we talk about quality, there are different aspects as we talk about what is that quality attributes in the first 2-week lectures. Do you remember? We talk about functionality, we talk about reliability, usability, maintainability, portability, efficiency. So different aspects have different measurement as well. And then how can we measure it, right? That's a key question, okay? And then because in reality, there are lots of metrics, we need to select the right one as well. How can we, let's say, if we want to measure the quality of the product, how should we measure it? Should we measure based on the lines of code or not? Probably no, right? Large code base doesn't mean that it contains lots of bugs. Is that right? Should we use the psychrometric complexity or not? Probably yes, probably no, right? It really depends, because if we use a psychrometric complexity, despite the code is highly complex, lots of if conditions, lots of while loop, but it doesn't mean that the code is poor quality, you know? There might be other factors as well. So what I want to say here is that normally we use a combination of metrics together to make a decision whether we ready to release the software or not, right? And yeah, these are some of the metrics that we're gonna talk about today as well. Complexity metrics, testing metrics like test coverage, test effectiveness, defect detection percentage, test execution effort, that kind of thing, blah blah blah. Okay, psychrometric complexity. Okay, I maybe I should go back to this one a little bit, right? What I want to say here is that that there are a few more metrics I should mention as well. Like this one, when we look at the reliability of the software, there are a few more metrics. If you Google in the Wikipedia, or they are used in large scale software system as well. For example, the mean time to failure, the reliability of the software, reliability index, that kind of thing. You can Google a little bit more as well. So those are the measures that they are used, okay, nowadays. And what else? Yeah, I think because we have four aspect here: project, product, people, process. Maybe at the beginning I will focus on the product metrics. Okay, product metrics. How can we measure the product? Okay, mainly we talk about lines of code, the size of the products. Psychrometric complexity is about the complexity of the software programs, and there are different types of the code complexity as well. For example, McCabe psychrometric complexity, the Halstead complexity metric, or the OO program metrics as well. Okay, so the first one, lines of code. I think everyone knows that what the lines of code mean. Just count basically how many lines in code. But actually, I should measure one more thing, that there are different types of the lines of code as well. For example, the physical lines of code and the logical lines of code. Okay, physical lines of code mean given a program, how many physical lines are there. Let's say if there are 20 physical lines of code, it count the blank space, the blank lines, the blank lines, the comment lines, everything that is executed or not executed, they just count everything. Okay, there's a physical lines of code. But in the assignment tree, assessment tree, as you remember, there's a one question that talk about the logical lines of code. It means that any lines of code that can be executed. So it means that we normally do not count the blank space, the blank lines and the comment lines when if we talk about the logical lines of code. Okay, these are the two key difference between what is the physical lines of code and the logical lines of code. Okay, psychrometric complexity. Normally we use to measure the complex of the code. Okay, the complexity of the code. And there are different types of the code complexity as well. For example, the first one we already mentioned about. We are familiar with this one. It's called McCabe psychrometric complexity, which is introduced in 1976. Okay, basically it measures what is the independent part in the program, right? And when we talk about the independent part, it means that it is a part that has at least one edge, which has not been traversed before any other part. Okay, and normally to measure this one, what we did in the past is that we draw the control flow graph first. Okay, we draw the control flow graph and then we count. We have a formula. Okay, to count what is it, how many edge, how many node, and put that into the formula and compute it. Okay. Okay, yeah. So what I want to say is that normally there are three formulas here. Okay, the first one is based on the node, the edge connected component. Another one is based on the numbers of the decision point, and the last one is based on the numbers of region. Probably you have read in the ED step before. Let's give a more example. Okay, this is the first formula, which is based on the numbers of edges and the numbers of nodes. Okay, so VG which is equal to E minus N plus 2P. Okay, E stand for where E is the numbers of edges and the N is the numbers of node and the P is the numbers of the connected components. Okay, like in this one, this is a simple program. Get the pen here. Let's say this is a control flow graph, right? And then we're gonna count, okay, how many edges, how many nodes, okay? So look at the edges, how many are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 edges here, and how many nodes, right? 1, okay, 2, 3, 4, 5, 6, 7. Okay, so in this case, there are 7 nodes, and when we apply to this formula, okay, then 9 minus 7 plus 2, in this case, the cyclomatic complexity for this code is 4. Okay, does that make sense? And normally, what I forget to say here is that when we develop, when we set up a software development project, right? Normally, we in the QA plan, normally we need to set up a threshold, okay, to assure the quality of the software system. Let's say project manager may set up and say that, okay, based on our code base, we want to ensure that the cyclomatic complexity for every program should be less than 5. The lines of code, it should not be greater than 1,000 lines of code, that kind of thing. OO metric should be something like that, right? And once we set up this kind of measure, we can integrate it into the CI and the CD pipeline as a quality gate as well. So that means whenever the commits happen, when you commit the code into the repository, right? So the CI/CD can be a quality gate to check whether the piece of code that you commit exceed the metrics that you have that we set earlier or not. Okay, that's how we use the software metrics in practice. Okay, yeah. All right, that's a McCabe cyclomatic complexity. But let's say if we use another what is that, the another formula. For this one, it is based on the numbers of condition node. Okay, VG equal to tau plus 1. This one, the numbers of condition node. Okay, so in this case, how many decision node? When we talk about the decision node, is like a if else that kind of thing, you know. So A, this is a decision node because it has 2 branches. Okay, C, yeah, 2 branches go to D and E, and the last one is a G, right? If else, okay, yeah. So in this case, we have 3 decision node plus 1. Okay, so that's the formula, and then it equals 4. Okay, actually, not G. I should say E is the E. Okay, apologies. Yeah. So this is the condition node. Okay, A, C, and E. Okay, E. This is the branches. Okay, just want to clarify. Yeah, that's the decision node. Okay, yeah. So in this case, we have 3 decision node plus 1. That's why we get 4, which is the same as the earlier one, right? Okay, and the next one, which is based on region. Okay, region. What does it mean, region? The area. Okay, so in this case, okay, get the mouse. Yep. In this case, there are 4 regions. Okay, numbers of regions mean the closed area here. This is the region number 1. This is a region number 2. Okay, and this is a region number 3. Okay, and the outside here, yeah, the region number 4 in total. Okay, so in this case, there are 4 regions. They're the same regardless of the formula. Okay, you will get the same cyclomatic complexity. There are just different ways to compute. All right, that's the region. Okay, now we talk about the lines of code already, the size of the code, the complexity of the code. Now we're gonna look at the design of the code, right? When especially the OO metrics are especially important for the object-oriented programming languages like Java. Okay, Java normally it is developed as an object-oriented, and we the OO concept, we talk about this one, right? Encapsulation, abstraction, polymorphism, inheritance, class, object, or whatever, and then we're gonna measure how good is the design of the software programs, right? So these are the 6 OO metrics which are proposed by Shidamber and Kammerer. Okay, people often call CK metrics. Okay, CK metrics. They are proposed like 19 something. Okay, The first one normally is called weighted methods per class, depth of the inheritance tree, numbers of children, coupling between objects, okay, response for a class, lack of cohesion in the method, okay. These are the class diagram. If we gonna look at it one by one, right? So the first one, weighted method per class can be measured using this one. So basically, it is a summation of the numbers of methods, okay, and the complexity of the methods involved in the predictors of how much time and effort is required to develop and maintain and reuse it. Okay, it means like this. Okay, normally when we write a Java class, this is a class. Okay, yeah, and there are lots of method here. Is that right? Okay, because the cyclomatic complexity cannot be measured at the class level. It has to be at the file level or the method level, right? So that's why they first compute the complexity, okay, for each method, okay, here, and they aggregate it. They do the summation of everything here, of the complexity here, as a to be the complexity at the class level. That's it, nothing more than that. Okay, that's why it's called sum of the complexity of the method here. Okay, that's the metric. This one, weighted method per class. Okay, yeah. So in short, weighted method per class is the sum of the complexity of all of the method in the class. Okay. Depth of the inheritance tree, right? When we decide the class, decide the object-oriented programs, when the class is really dead, okay, have a big hierarchy, then it becomes even more complex, right? So this one it becomes very difficult to maintain. That's why normally we use this as a measurement, okay, depth of the inheritance tree, okay, how depth it is, okay. So first object, this is the object, that's the level 0. If you have another object, another class that inherit the object here, this one, the depth becomes 1. And if you have another one, right, that's the depth is the 2 now. And if you have another one, yeah, you have another, then the depth will be 3 levels. Okay, so when you have this kind of hierarchy, the program is very hard to maintain. That's right. Sometimes people just set the depth inheritance to become only 1 or 2, that kind of thing. It should not be more than 3, right? Okay, so this is a measurement, and the intuition behind, I should say that, let me put this way. When you come up with a metric, right, a measurement, you should have an intuition behind. For example, go back to the first one. Okay, lines of code. Larger lines of code tend to have a risk of having defects. Okay, bigger products, nothing more than that. It's about rationale. Okay, it's about tendency, likelihood. And what about code complexity? The code that is has a higher complexity are likely to be defective in the future as well. The weighted method per class, this one, because the class is getting more complex, there's a higher chance to be defective as well. Same to this one, when the class is designed with too much depth of inheritance tree, then there's a higher chance to be defective in the future as well. That's why they try to keep this kind of metric as small as possible. Break it down right in the atomic unit, that kind of thing. Okay. Numbers of children. Okay, children. This one is about OO as well. If you are familiar with, we have a parent class, and these are the children class. Okay, how many children are there? Okay, children. Numbers of children. So in this case, okay, object has only 1 child, okay, widget, right? And the widget has 3 children. Window, canvas, and the layout. And the layout has another 2 children. Horizontal layout, vertical layout. So when you have high numbers of children here, so in this case, the class has a total of 3 plus 2 plus 1, so it becomes 6. Okay, 6 children, right? this object has 6 children. That's a lot. So it means that when you have a high numbers of children, it means that good reuse, but very bad abstraction. Maybe you reuse the code a lot. You inherit the properties from the parent class, but the way you abstract the class is a little bit maybe not so good. That kind of thing. Okay. Yeah, numbers of children. Coupling between objects, right? When you design object-oriented programs, it should achieve high cohesion but low coupling. Okay, the high cohesion and low coupling. The code should not be coupled together too much. Okay, so that's why they come up with this measure CBO. Okay, coupling between objects. It measures the numbers of classes that are coupled to a particular class. Okay, and couple, what does it mean, right? It means that where the methods of one class call the methods or access the variables of the other. Okay, so there are so many methods calling with each other too much, right? If you look at the figure A here, A, B, C, okay? A, it means that each of the method here, each of the module has no dependency at all. They don't call each other, okay? It's low, it means that it is low coupling, okay? I should say zero, not just low, okay? B, there are some dependencies, right? A call B, B call C, C call D, that kind of thing, okay? It has some dependency. But when you have C like this, it means that the when we decide the class, it is not so good at all because it is highly coupled. There are too many dependent. A call B, B call C, C call D, D call A, B, C, and call everything is like all over the place. That's not the way we decide the objects, right? So when the code is highly dependent like this, it's really difficult to maintain, right? If you change one thing, the other place need to be changed as well. If you change one variable name, the other place need to be changed as well. So that's not a good way to decide the class at all, okay? Response for class, okay? I'm gonna skip some of these, okay? Maybe I should not skip, yeah. Go back to this one. Response for class, okay, what is that? It means that all of the methods in the class and all of the methods that are called by matrix in that class, okay? So if a large number of methods can be invoked in a response to a message, I think this is about, yeah, I think I should skip this one. Yeah, okay, lack of cohesion. So we will not focus on the OO matrix in the unit anyway, okay? And this is a summary, right? Summary, we have the weighted method per class, depth of inheritance, numbers of children, CBO, that kind of thing. And the goal here, it means that we should keep it low or should keep it high, that kind of thing. So the complexity, WMC, we talk about the summation of the complexity. We should keep it low as much as possible. Depth of inheritance is a trade-off matrix, right? If you have a high inheritance, it means that you have a good reuse of the code, but at the same time, the class is really complex as well because it has too much inheritance. Okay, that kind of thing. Yeah. So it's a trade-off between the complexity and the reusability. This is something that we need to consider. Okay. In addition to the OO matrix, right? In terms of the software testing, we can also measure as well. For example, we use the code coverage before. Basically, it measures the completeness of the test cases, right? Because you have 100 lines of code, the code coverage measures how many lines in the program that are exercised by the test cases. Ideally, the code coverage should exercise all lines of code. It means that the test cases are complete. But when you have the complete test cases, it doesn't mean that the program is free of bugs. Because in the week 2 or week 3, intro to software testing, we talk about the one of the quote before that testing only show the presence of the bugs, but not their absence. Okay, so you write the test cases. It doesn't mean that you write the test cases, you achieve 100% code coverage. It doesn't mean that you can the program is free of bugs. Okay, it doesn't mean like that. Yeah. And there's another measure as well. Okay, normally it is used to measure the effectiveness of the test cases. Okay, Yeah. Measure the effectiveness of the test cases is called mutation score or mutation testing. What does it mean is that normally when we write the test case, good test case should be able to detect the bugs if the code is slightly changed, right? Let's say if you want to, what is that? Come up with a test case to test the add function. Normally 1 + 1 = 2. Is that right? 1 + 1 = 2. And when we with the mutation testing here, okay, I should write this one a little bit. Okay, let's say you have the add function here. Okay, that take the input A and B and return something. The first test case. Okay, the first test case. Number one, let's say we put 1 + 1. Okay, it should return 2. And this test case, is it good or not? Because it is good. Let's say that the goal of this one, they want to inject the bugs into the program by slightly change the program. Okay, slightly change, introduce the mutation. It means that, for example, change the arithmetic in the programs. Okay, let's say if we change instead of A + B, I change it to A - B, right? And if we run the same test case, whether the test case is fail or not, yes, that means this test case is good, because this test case, it captures the requirement here, because we want to test the add function. But let's say if I have another test case, okay, 1 second. If I come up with another test case, okay, number 2 here, I have 0 + 0 = 0. Okay, A + B, 0 + 0 will get 0 or not? Yes. A - B, 0 - 0 will get 0 or not? Yes. In this case, it means that the test case cannot detect the bugs at all. That means this is a very bad test case, and we should not have it in the program, okay? Because it tests nothing, you know? Does it make sense, everyone? And to measure the effectiveness of the test case, normally people use a mutation score or the mutation testing. And there's a Python package available here. Everyone can use MuPy, okay? Yeah. Am I going too fast or not? Maybe if you have any questions, please feel free to ask me. Okay, next, testing metrics, right? And then we talk about the product metrics already. These are the metrics we use to measure the product, the size, like the code complexity, or whatever. This is more about software testing process, the quality of the test cases. And now we're gonna talk about the process, right? We measure the process just to let me put this way. I should say this earlier as well. The key application of the software metrics is normally we want to predict the software defects. Okay, measure the quality of everything, quality of the product, quality of the process, quality of the people, quality of the project. Okay, measure the quality. Everything is about quality. How do we know whether the process that we have at the moment is good or not, right? We need to measure it, and we can measure by the numbers of commit. Okay, measure by the numbers of line added, measure the numbers of delete line, how many developers are there, how many distinct developers at the project level or whatever. Okay, let me put this way. And this is the ownership metrics as well. So the intuition here is like this. Let's say we talk about the files. Okay, this is a file a.java. Okay, a.java. Think about if this file have 1,000 commits touch this file, what does it mean? It means that this file has too many changes, right? So there's a higher chance that this file will be buggy in the future. Intuitively, by the intuition, common sense, what's wrong with this file? Why this file is changed greater than the others. Okay, if you measure the numbers of commits that are associated with each file, okay, and if you plot the bar chart here, you will know, okay, like which files are greatly changes and which file have never been touched at all by the developers or that kind of thing. Okay, so with this kind of analysis, right, you can identify what are the risky area, what are the hotspot area that are likely to be defective in the future. Okay, that's the numbers of commit. Oh, all right, and another one, add lines and the delete lines. Okay, let's say if this one is at the, let's say, I think this is similar to the, no, that's a commit, right? Let's say this is a a.java again, okay? A.java, if there are too many commits, okay, that's a higher risk already. But let's say if this file, okay, a.java has too many add line, has too many delete lines, right? Then the key question is that when the file keep changing like this, are they well tested or not? And because there are too many changed lines in this file, again, there's a higher chance that it will be defective in the future as well. Okay. What about the numbers of developers? Okay. Let's say a.java again, and this file, given this particular file, has 10 developers. Fix this file, working on this file, the same file, right? And what about the other files? They don't touch it at all. So probably this file is too large or not. Should we break down to reduce the numbers of developers or not? Intuitively, different developers have different coding style. You know how can, and then when one particular file have too many developers working on it, then there's a higher chance that the file will be conflicted, the inconsistent variable names, coding style, or whatever. So it becomes even harder to maintain, right? So when we use this kind of measurement, okay, to measure each of the file here, then we can identify where are the risky area of the code base. Okay, make sense? Yeah. Okay. Code ownership. Okay. What does it mean? It means that we want to measure who own the code. That's it. Easy like that. And the ownership of the code can be measured in two ways. Okay. Normally we use the commit level or the line level. Given a particular file, if this file 95% of the lines of code are written by the developers A and the other written by developer B. So because A wrote most of the code in this Java class here, so A should be the owner of this particular file. Okay, this is how we measure based on the lines. But if we talk about the numbers of commit, then we talk about who are the developers who contribute the most. Okay, measured by the numbers of commit to this particular file, that kind of thing. Okay, make sense? This is how we identify how many major developers, how many minor developers to a particular file, that kind of thing. Okay. Okay. Yeah. And in addition to the process metrics, right, we can also measure the code review process as well. And let's take a look at an example here, right? For example, the numbers of concurrent review. This is at we look at the human factors. We look at the workload. Okay, so the rationale here is that this is for each reviewer. A reviewer who is burdened with large numbers of review tasks may not have time to review a patch. It means that when we want to measure the effectiveness of the code review process, let's say you have a process and every pull request you just assign to only one single developer, then their workload is quite burdened, right? So it's not normally distributed to everyone. That means that particular reviewer will have a very high numbers of concurrent reviews. And then the key question is that would the review from that developer, from that reviewer, will be of high quality or not, right? So probably no. That's why we should measure this kind of aspect to ensure that the process is, how can I say, it has a good health, Okay. That's the numbers of the concurrent reviews for each of the reviewer. Numbers of the remaining reviews as well. For a particular reviewer, how many reviews are remaining? They have been assigned already, and what is the remaining? If it is too high, is that a good reviewer or not? That kind of thing, okay? We can look at the social interaction. We can look at the review experience. For a particular reviewer, how many lines that they have reviewed in the past, okay? And we can look at the patch size as well, okay? For a particular pull request, whether the size of the pull request is too large or not, is it too small or not, that kind of thing, you know? There are so many ways. This is just an example, okay? So many ways to measure the process. And that's a code review, okay? And I'm gonna show you, this is an example, right? How can we apply the software metrics in the real world scenarios? And this is a very good application from Microsoft Research, okay? So they use this kind of software metrics to predict which file in the code base or which commit are likely to be buggy in the future, okay? So they just use AI and the machine learning model. Maybe I will open some video, okay? Yeah. So basically, just click this link, okay? Microsoft AI Lab Code Defect. So everyone will get an idea.
Code defect prediction is a solution allow developer to find bugs early in the development lifecycle.
In software engineering, developer writes code and then checks in their code in a version control system such as Git. Testing teams uncover bugs and post these bugs in a defect management system so that the engineers can go in and fix the bug. The process repeats itself a number of times until the code becomes stable and resilient. This back and forth process is very costly. It would be tremendous value if we were to cut the number of these cycles. Customers who have used our code defect prediction solutions are able to identify over 20% of the defect before even the testing phase begins.
Altron is a worldwide leader in engineering and R&D services, and being a services company, we always look for options to enhance our developer productivities. We started this project and discussion on how we can integrate code defect prediction on AI Lab.
We first extract historical data. We apply our algorithms to find the patterns. We use machine learning techniques to analyze testing assets and source code patterns to predict the likelihood that a code change is potentially buggy. Moving forward, we want to couple our code defect prediction with our test case selection. The solution will identify areas of the code that are potentially buggy and then suggest a set of tests to run against the latest code changes in order to maximize code coverage and increase the product quality. We're going to be displaying this solution very soon on the Microsoft AI Lab portal so that Microsoft developers can download the solution and use it internally.
That's right. Okay. So that's the applications of the defect prediction. Okay. And basically, this is my own research area. If you are interested, feel free to talk to me as well. I also wrote a book here, Explainable AI for Software Engineering. If you go through the defect prediction models, part 2 here, it will tells you, give a very detailed background. Why do we need defect prediction? What is the software quality assurance process? And what is the problem at the moment, you know? And how can we build the defect prediction models, okay? Briefly speaking, so I would say that start from the GitHub repository here. We need to collect the data. we cleaning the data, extract the metrics. That's what I mentioned before. Okay, so we use lots of product metrics, process metric, code ownership, and everything. Okay, to predict the outcome. That's the numbers of the defect that we want to predict, and we can do the data resampling. Okay, sampling the data, split the data into the training and the testing. We build a machine learning model, evaluate the model, and then predict why this particular file is being defective in the future. Okay, does that make sense? And this is just an example. You know, this one we want to not just predict whether this is beyond just predict whether this file is buggy or not, right? Like, no, sorry, this one we run the prediction model on the project. This one Apache Camel. When we look at the file here, the model prediction will say, yes, this file is likely to be buggy in the future with a risk score of 70%. And it also tells you which lines of code that are likely to be defective in the future as well. And we can also explain as well why this file is likely to be defective in the future because of which metric, right? Class method, LOC. That means what is that? It measures the numbers of lines of class and method declaration, right? So the class lines of code here is too large per method, that kind of thing. So it contributes the most to the prediction risk, the risk of defect, right? So that's why we should reduce the lines of code as much as possible, that kind of thing, you know. And developers can also they can try as well, like okay, this is too complex now, I'm gonna skip. Yeah, makes sense, everyone? Do you have any other questions? Yeah, so okay, we have one student asking about the mark. Yeah, we're gonna release it very soon. Yeah, okay, all good. I think that's all for today, and I hope to see you in the studio afternoon as well. Yep. All right, thank you so much. Yeah, thank you for your attention. Have a good day. Bye bye.